So today we discuss carbon resistor. So new topic is carbon resistor. What is resistor actually? In daily life, there is a switchboard, circuit board in our home, office, school, college. There is an important device is called resistor. Without resistor, I think there is a little bit problem to build a circuit because the basic component of that circuit in our home appliance, either college, school, traffic signal, the basic component is a resistor. Okay. Here is available in market. This is a resistor name is called carbon resistor. It's called carbon resistor. And here is some calculation how to calculate carbon resistor value, how much ohm. So there is a color code is called color code. Okay. So there is a first color is called black. Black. Next is brown, red. Next orange. There is the orange. Okay. Orange, yellow, green, blue, violet, gray and white. Gray and white. These 10 colors, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So black has code is 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, gray 8, white 9. Okay, how to remember that codes? Okay, so black B, brown B, red, okay, orange, sorry, red, orange, yellow, green, blue, violet, gray and white. How to remember? There is a code, a cheat code to say that. This a cheat code is BB Roy, BB Roy in a good batsman is a good batsman and very good wicket keeper and very good wicket keeper. Okay, so you see that cheat code here. B for black, next B for brown, Roy, red, O, orange, Y, here's a Y, B, Roy, black, brown, red, orange, yellow, again good, G, green, batsman, blue, and there's no point here. A very V, violet, next gray, good, wicket keeper, there's a white. That's a cheat code. Okay, remember B Roy is a good batsman and very good wicket keeper. That's the cheat code for remember of the color code of a carbon resistor. Okay. So how to look like that resistor? There is a cylinder type. Okay. There's a two terminal. So resistor has a non-polar. Okay, there's a no polarity, either plus, minus. If you choose, if you want to choose. So resistor has no polarity. Okay, so there is a band. There is a band. There is a band. There's the first band, second band, third band, and here the other band. there is a 4 band. Okay, there is a 4 band. First band, the color of the band. Actually, there is a color of the band define the values of the resistor. First color, second color, third color, there is a fourth color, and these fourth color, fourth band represent tolerance. Okay, tolerance. For there is a two color, either gold and silver, fourth band. If gold, so plus minus 5% tolerance for gold is gold color, not actually gold. There is a gold color. Okay, if there is a gold in resistors, that's not actually color is gold, and it's a plus minus 10%. The color is tolerance color is silver. Okay, and how to define that color and calculate the values. Okay, suppose the first color we say red, orange, yellow. Suppose that is a red, that is a orange, and that is third color is yellow. Okay, and how to define? First color red, code is 2. The 2. Second color is orange, so there is 3. And third color, actually third color is 10 to the power yellow. Yellow means 10 to the power 4. And if a fourth band is called gold, so that is a plus minus 5% tolerance. That's the ohm. So finally we get 230 plus minus, okay, kilo ohm plus minus 5% up and down value. Okay, so that's the important to find the resistance value in commercial available. Actually, carbon resistor commercial available in switchboard, circuit board, in any other circuit. The basic component is carbon resistor. The resistor is a basic component in our daily life. Okay, if you see your home switchboard, home appliance, there is a one resistance. Okay, resistor is here. Now, the temperature dependence of resistivity. Okay, so next point to discuss, temperature dependence of resistivity. Okay, so there is a formula, rho tau, that is equal to rho 0 1 plus square bracket 1 plus alpha T minus T0, where rho T, that is equal to resistivity at any temperature, resistivity of temperature T. Okay, and some dash value of T, suppose 10 degree, 20 degree, 30 degree, that is depending on what we value want to choose. Okay, next is rho naught. Rho naught is the resistivity at a reference temperature. Resistivity of reference temperature. Reference temperature is T naught. That's a reference. Okay, that's a reference temperature. If you choose a reference value or mean value, then calculate up, that's a higher temperature, that's below the reference is the lower temperature. That is your user hand if you choose any values. Okay, and what is the alpha? And alpha signifies, the very important is temperature coefficient. Coefficient. Okay, and the dimension is very important. The dimension is temperature to the power minus 1. That's the dimension, and there is a temperature coefficient. Okay, so here the important fact is that different material does not exhibit the same dependence. Okay, so different material does not exhibit the same dependence of the temperature over the limit range of temperature. That's a very important key point is, okay, the different material So actually different materials show the different resistivity, and different temperature also show the different resistivity. The different material does not exhibit the same dependence of temperature. The same dependence of temperature, okay, over the limit range of temperature. The important is over the limit range of. That's a very important point. Here are some graph, okay, graphical representation. Like here's a three graph of. There's the first graph, okay. There's the resistivity, and the resistivity of suppose copper, okay, and that the temperature in Kelvin scale. Suppose resistivity of copper is that is equal to 10 to the power minus 8 ohm meter. So if you want to plot that, suppose 50, 100, 150, that is a 0.2, and here suppose the 0.4. Okay, so temperature versus resistivity plot of copper metal actually look like this. That is a little bit curved. The more temperature here means a more resistivity here. The temperature increase, the resistivity also increase. Okay. So another important for in called night chromware. If you want to plot copper versus temperature plot, if you now change the temperature, suppose they are in Kelvin, and resistivity of night chromware. Nichromware, and so that is suppose that 200, 400, 600 and 800, the temperature in Kelvin, and that is 1.1, 1.2. Okay, so in nichromware, that's they obviously increase, but they are not exponential, they are the linear expansion. They are a linear expansion, very important. For nichromware, speed of nichromware versus temperature, they are the linear expansion. So show that here, look, same temperature, they are the increase, but different way actually. Okay, they are not the same actually. Okay, suppose now be the semiconductor. Now another is semiconductor. Temperature in Kelvin, but rho now change being semiconductor. Suppose a silicon diode or any other semiconductor device. So here the graph is look like this. Okay. If temperature increase, the resistivity is decaying. There is a typical semiconductor, temperature is increased, so resistivity is decaying. That is a typical semiconductor nature. That is very important. Okay. The clear the how why I said that the different material does not exhibit the same dependence of the temperature over the limit range of temperature. That's the plot. These plot satisfy that statements. Okay. And now there is some basic calculation or concept here. The rho that is equal to resistivity is 1 over conductivity. That is equal to mass of free charge carrier, either electron or proton. The number of charge carrier per unit volume, that is n, number of charge carrier per unit volume, E square elementary charge, and tau is the average time or average collision time, tau. And you see that equation, the resistivity is inversely proportional of n, and resistivity also inversely proportional of the collision time. These are the collision time, average collision time. Okay. That's very important. These two, they are reciprocal. The N is the number of free charge carrier per unit volume. Number of free charge carrier per unit volume. And as the increasing temperature, there is some concept here. Note the very important concept that as the increasing temperature, as the increasing temperature, say that this temperature is increased, the average speed of electron, so average, the important average speed of electron, actually average speed which act as a carrier of current. So average speed of electron is a act as carrier of current. That's important. Okay, charge carrier current. If they increase the resulting more frequent collision. If they actually means the average speed is increased as the increase in temperature, the more frequent collision, the increasing current, increasing resulting in more frequent collision, in more frequent collision. If more frequent collision, tau is decreasing. So average times may be decreasing. Okay, so tau is decreasing. If collision increase, the gap between two collision is really decreasing. Okay, so average time of collision. So that tau is the average time of collision. Collision. The collision is decreasing. Okay, so tau. Okay, that's the inversely. So the tau as inversely proportional of temperature. So here the temperature is increasing. As the increasing temperature, so tau is decreasing. So they are inversely proportional here. But there's a metal, obviously metal. Now in case of metal, that's important. In N, actually charge carrier per unit volume, the N is not dependent on temperature. On temperature of any appreciate extent. Okay, on temperature to any appreciable extent. That is important. And these decreasing the value of tau and these the decreasing values of tau for rising temperature. For rising temperature. Okay. So tau is decreasing. So step is tau is decreasing. And next step is temperature increase. Temperature increase. And the next step is rho increased. Okay. Rho that is the block diagram. Okay. In insulator and semiconductor, the important factor in insulator as a metal, but in insulator, in insulator, or semiconductor, insulator or semiconductor. Okay, n directly proportional to T. So means that if n is increasing, so temperature obviously increasing. So temperature increasing means n increasing. So this is the increase more compensate actually the decrease in the tau. Okay, actually say material. So or you see that is rho is inversely proportional of T. So if rho is temperature is increasing, so rho is decreasing. So if temperature is decreasing, so rho is here increasing. And temperature is also directly proportional to number of free charge carrier per unit volume. Here the key point is this increase more. So this concept increased more than compensate than set. Okay, and set any decreased in tau, any in tau in such material, such material show that property. Okay, so if temperature increase, there is a more number of free charge carrier per unit volume is moving. Okay, that's the very important, and that is a more charge are moving means that tau resistivity, says resistivity is here. If temperature increasing, resistivity is decreasing. Okay, and if resistivity decreasing, so obviously R decreasing. If R is decreasing, current is increasing, and we know that the concept. That's the basic concept of a resistivity. Okay, and okay, I think there's a clear the concept what is resistivity and dependence of temperature of resistivity and how resistivity related to the resistance. Okay, because we know that R equal to rho L by A. So R is directly proportional to rho here. That's important. Other two factor obviously here, the length of conductor, cross section area of conductor. But I say that if these two are constant, so rho is directly proportional to R. Okay, so they are directly proportional. And R in from Ohm's law, they are inversely proportional to current. So if R is decreasing, okay, temperature increasing means resistance decreasing. If resistance decreasing means resistance decreasing. If resistance decreasing means current increasing. So current is directly proportional to Q by T. So actually charge increasing. So that clear the concept. That means charge. Here number of free charge carrier per unit volume here. So that's obviously increasing the value. Clear that the circle of that concept. There's a circular concept. Okay, they are related to one, related to other. If you clear the concept, that's a very easy concept actually. Very easy concept, and if you remember that concept, so a very small trick you can apply, and you clear all question. You can answer all basic small to small conceptual question. Okay, that's very important. Clear the concept and read the books very carefully. If you choose any book, either NCERT, either Newton, H.C. Verma, any book, yeah, Resnick Halliday, all books are genius. All books are best books. But if you want to read them A to Z, top to bottom very carefully, you read the all question in board exam, and you get 100 out of 100 is not impossible. It's a possible. Okay. Next, we discuss that another important concept is the electrical energy and power. Electrical energy and power. Okay, so there is a conductor. There you choose a conductor. Suppose that's a point here, that is a B point here, or A terminal, or that is a B terminal, A port or B port. Potential here at A port is VA, potential at port B or point B, that is a VB. And if you say that is say, let's say assumption VA is greater than VB. Okay, VA is greater than VB, and number of charge carries from VA, that is Q, and from VB, that is also the Q. The same charge carry here. So potential energy, that's the important parameter, is potential energy at A. From previous chapter, we know that is Q times VA, and potential at point B or port B, that is equal to Q free charge carrier times VV. Okay, and if you say that A greater than VB, so charge carrier, if I choose the electron, okay, if you choose the electron move from lower potential to higher potential if you choose the free charge carrier with the electron, or if you choose the free charge carrier with the proton, so proton move from higher potential to lower potential. Clear the concept is what is the higher potential meanings and what is the lower potential meaning and how to relate it for free charge carrier. Okay, so VA minus V, that's the potential difference, and that is VA minus VB. Okay, if I choose a charge carrier with the electron from lower potential to higher potential, so potential difference is that final potential minus initial potential. So here say free charge carrier with electron, we choose that. Okay, and that's the greater than 0 obviously. Okay, now the same some time interval delta t, the some time interval delta t, the amount of charge flow, the amount of charge flow through a conductor is suppose called delta q, and that delta q from Ampere's law, that is equal to charge by time equal to current, so I times delta t, because you know that I equal to q by t, so q equal to I times t. And the travel from, if a charge carry travel from, is a current, means suppose travel from A to B terminus, current moving A to B terminus. Okay, so now here the important is the potential energy difference. Okay, that is delta U potential energy difference, that is equal to UB minus UA. So if I choose say that here the current or proton move from A to B. Here choose the proton move from A to B. Here to move from B to A. But now if I free charge carrier proton is moved from A to B. So from potential concept. So final potential minus initial potential is a proton free charge carrier here. Okay. Suppose that's not free charge carrier. Suppose this now changed to proton. Change to proton. Change. Previous that the potential difference. Okay, VA minus VB, higher potential minus lower potential. Okay, means the potential difference is that. Okay, so here if you free charge, we now choose the proton. So potential energy, that is equal to changing potential UB minus UA. Here UB, that is equal to QVB minus QVA. Okay, that's basic mathematics. So Q common, VB minus VA. Okay, now here you see that is a form choose when I choose that is an electron. So changing potential means higher potential minus lower potential, VA minus VB, because that is a higher potential, that is a lower potential. So that's why here it doesn't matter what type of charge carrier you choose, proton or electron. That's the gap between these. That okay. Here the actual current moving. Here the important is the current direction. Important is current direction. So that is minus Q VAB, because VA minus VB, that is a less than 0. That's why okay, negative. So that is a U potential energy, and Q equal to, we know that minus I delta T VAB less than 0. That's a minus sign here. Okay, if a charge moves without collision, Okay, there is some condition. If charge move, if charge move without collision, okay, without collision throughout the conductor, throughout the conductor, that is actually means no collision without the conductor. So kinetic energy could also be changed. So kinetic energy would also be changed. Okay. So that means the total energy obviously change, means that the T change, total energy also will change. That is delta K, that is equal to minus U potential energy. Due to the conservation of energy, total energy with the conserved. Okay, delta K plus delta U, that is equal to conserve some constant value. Okay, so here for delta K, now that is a U potential, we get a minus. That's minus, that's minus, they cancel each other. So we get I delta T times VAB. That's the greater than value. So if potential energy is less than 0, kinetic energy is the greater than 0. If I added these two, so get it 0. Okay, there is a 0 energy change here. So delta K greater than be the 0. So there is a total charge move in a conductor. So kinetic energy obviously change. Okay. So here the total energy change. Okay. Now if the total charge, so there is some block diagram here. Suppose draw the block diagram like if the total charge, the total charge move in conductor, move in conductor. Okay. So kinetic energy change. Okay. So if the kinetic energy change due to electric field, why kinetic energy due to electric field? Okay. So now electron are accelerate. Now electron are accelerate. Okay. If electron are accelerate, the important is that so means more collision. So means more collision. So here the more collision, the importance more heat. So more collision generate to more heat. Heat is another form of energy. The total, the amount of energy means either heat energy dissipated at heat. So finally, conclusion is that the amount of energy, finally, the amount of energy dissipated, heat energy, form of heat, form of heat energy. Okay. So now we know that work energy theorem from class 11 or class 10, the delta W, the work energy, that is the work done equal to change in energy. So that is equal to, we both unit are joules. So W equal to I delta T times VAB, or you say that is VAB times to V. So IV times delta T. That is a from work energy theorem. And from work energy theorem, the change in energy, that is equal to work done. So delta W by delta T, okay, that means actually the time, that's not time, okay, not temperature. Delta T, that is equal to I times V. So delta W by delta T, we know that that is equal to power. So P equal to IV or VI. That's the power. And this is actually the ohmic loss. The power is lost due to the heat. Okay. This is a power loss. These power actually be the losses. The power loss represents the power loss from the heat energy. The another name is called ohmic law. Ohmic laws in a conductor. In a conductor of resistor R carrying a current I, the power which is heated up, the power is heated up. Okay, like the some example is like a electric bulb. Okay, the tungsten bulb, the more current is more heat. Okay, that's a basic example. So that is actually a loss, but we use that loss in our daily life for like electric heater, induction cooker. Okay, we use that loss also. Okay, sometimes we use that loss and use for our daily life. So physics actually are related to our daily life. Okay, that's very important point. Okay, so that's very important. Physics is our need in our daily life. So do not ignore the physics concept. Okay, they are related to day-to-day life. So today wrap up the class here. If any doubt in any portion, ask in comment section. I will try to give the answer. So next class we discuss the new concept like combination of resistor in series, electromotive force, EMF, etc. Okay. So today in the class here. Thank you.